Greetings and welcome to a new video about extra element theorem. In this example, we will discuss another circuit, in this case an op-amp circuit having a capacitive feedback, and we will determine the transfer function for this circuit. In addition, we will also use the standard classical way of determining the transfer function for this circuit and compare the results. Okay, let's see what we need to do. In this case, we have an objective: use the extra element theorem, short EET, to determine the transfer function given A, which is then output voltage divided by the input voltage. And we have here the circuit. You see here the operational amplifier. We could assume it is ideal. The input voltage is applied in a non-inverting input of the op-amp. And we have here feedback, which is going through the resistor R3, the capacitor C, and the resistor R2. And we have the resistor here, R1, which is going from the inverting node to ground. And our output voltage is then here, VO. So what we need is, in the Laplace domain, again, the output voltage divided by the input voltage. So how do we work this out? Again, we start first with the definition or the expression of the gain using the extra element theorem. You see here a couple of parameters. First one is the gain defined for the Z is equal to infinite or approaching infinity. That is the Z, which is our extra element we will determine shortly or designate it shortly. The next one is the Zn, which is our nulling impedance. Zd is our driving point impedance, and the Z is our extra element as said before. In this case, we will designate our capacitor, C here, as our extra element. And now the impedance of that one in the Laplace domain, Z, is then 1 over Sc. Okay, so let's see the solutions. In this case, we will do the calculations first and use the extra element theorem. Step 1 is we will remove the capacitor C, that's our extra element, and calculate the voltage gain. And there we will determine actually this part of the expression. So we have this circuit, and you see here the opened capacitor, so that's gone. And we will here determine now the voltage gain. Now if you look at this, this is now a feedback having a series combination of R2 and R3. And the R1 is here coming from the inverting node to ground. And this is actually the non-inverting amplifier configuration we know from op-amp circuits. So we can easily determine here the voltage gain, which is then VO over VI, which is then 1 plus the resistors here in the feedback in series divided by the resistor going from the inverting node to ground. This is a standard formula, and we can use that here in this case. And that will be then defined as the gain for the condition where the Z is approaching infinity, which is our extra element. Okay, that was step 1. So let's also put that here. Step 2, we will now disable the input source. Now in this case, that is in voltage source, that means it should be shorted. Now we will then determine from that the driving point impedance, which is then ZD. Again, we will look between the nodes of the capacitor, which is opened. So the circuit will be like so. So the additional part here is that the VI is disabled or effectively shorted. So this is a wire. We will look again between the capacitor nodes here, C, and that is actually shown here. So this is the ZD. So how to determine here the driving point impedance? Well, more convenient way to do that is to, let's bring up another circuit, the same circuit again, and then put here a test source. In this case, I will apply here a test voltage source. I call that VD, and also designate the polarities. And also you have here an associated IT, which is our test current. And then the ratio VT over IT will be then using Ohm's law, the ZD. So we can say that ZD is equal to VT over IT. If I know that, I also know the impedance looking between these two nodes. This is similar to what we have done also with the Thevenin's theorem and Norton's theorem to determine the Thevenin resistance and the Norton resistance. So this is exactly the same procedure. So let's designate here the nodes. This node here, that is actually in this case 0 volts. Why? Because we have a negative feedback. So this operational amplifier tries to make this node voltage and that node voltage exactly equal to each other. Now since this is grounded for this condition, which is 0, this should be also 0 volts. Now, since that is 0, then the current flow in the resistor R1 should be also 0 amps. Why? Because this is 0 volts, this is ground, so the potential difference for resistor R1 is 0. So 0 minus 0 is 0 volts, divided by its resistance, which is non-zero value, so you get the 0 amps. Now, since we talk about an ideal operational amplifier, the current in the input terminals are also 0. So we have assume that the input impedance of our operational amplifier is infinite, so there will be no current in the terminal, so this is also 0. Now, since this is 0 in the R1, and that direction up in the inverting node of the operational amplifier is also 0, that means the current in the resistor R2 should be also 0, because that will make up these two currents. So we can say that is also 0. Now, since this is 0, that means the voltage across the resistor R2 is also 0. So we get actually this condition, which is then saying at that node, I can also say that I have 0 volts. Why again? Because this is 0. And the voltage across the resistor R2 is, using Ohm's law, 0 amps times the resistor R2 is also 0. So you get here 0 plus 0 is 0. Now if I look at now the VT, which is our test voltage source, you get here on top 0 volts and the bottom also 0 volts. So you get actually again a potential difference of 0, and that will be VT of 0 volts. But it doesn't matter. I mean, it doesn't mean that IT is also 0. That doesn't mean, because the current flow here is 0, but in this direction there will be some non-zero current. So your expression here will be then 0 divided by some non-zero value, which is then, of course, effectively 0. So we have a driving point impedance of 0 in this case. Okay. Step 3 is our null, the output node. That is the step 3. That means not grounding. So we will actually set this here. Let me go back here. So we'll make that 0 volts. And we'll determine now what we call the nulling impedance Zn, which is shown here. Again, we will look between the nodes of our capacitor C, which is our exit element. Now you see here again, the Vi is getting back in the picture. So we will not short that. Again, look between the two nodes of our capacitor, which is our exit element, and that is our Zn. And see here exactly the new condition, VO, output voltage is 0. So how do we work this in this case out? Well, let's bring up again this condition where the current inside the inverting node of the op-amp is 0. Now, since this is 0, we can say the following. We have here 0 volts, and this is looking now here in this direction. You have actually here a connection which is a series combination of R1 and R2, and you have on the right side a resistor R3 which is going to the 0 potential, which is exact same as ground in this case. So looking between the two nodes, the Zn will look on the left side and see R1 and R2. And on the right side, it will see the R3, and they are effectively parallel. So we can write now the Zn as the series combination of R1 and R2 in parallel with R3 in this case. Now we can also work it out in more detail. So we will get the product of the R1 and R2 in parentheses with the R3 divided by the summation. Let's bring now everything here. Now we have here the step 1, step 2, and step 3 results. Now we will apply, that's the step 3, use the formula here given and substitute the values we have found in step 1, step 2, and step 3. This is the formula again. Now you see here the 1 over Z, which is now substituted here from here, which is then SC. That's the only change we have made here. And we can now substitute here Zn, Zd, and A for the condition where the Z is approaching infinity. Now you see here this part is coming from here, so 1 plus R2 plus R3 over R1. That's this one. You have here 1 plus SC times the Zn, which is actually shown here. And you have also 1 plus SC times 0, which is Dd. So we will actually have here 0 plus 1, which is effectively 1. So you divide this by 1. Effectively you get now this result. You see here also clearly that this is a time constant, which is now in this case first order, and this is actually a differentiated circuit. Now the zero frequency here, because there's no pole, the only zero frequency here is determined by 1 over this time constant. And that is also, of course, a minus sign because it is on the left half plane. So you get here 1 over that is the flipping of this fraction, so R1 plus R2 plus R3 divided by this part. And that is now defined as the omega z, which is our zero frequency. But the more convenient way to write down the zero frequency is like so, 1 over the c times the zn, which is our nulling impedance, which is shown here. And this is actually much better to write down, so you can calculate also much faster your zero frequency. How about the DC gain? Well, if I look at the circuit, I mean the expression, but also the circuit, if this is DC is operating, so you have actually 0 Hertz, then this S is 0, so you actually lose this part in the parentheses. If only this 1 plus R2 plus R3 over R1, that is effectively what you see. You can also see that from the circuit, if the DC is applied, so DC sources, then this is an open circuit. You get exactly the non-inverting amplifier configuration we have found in step 1. So that's actually the expression which you see here. How about the high frequency gain? Well, if the frequency is much larger, so very large, then this is a short, because that's the impedance. And then you have actually effectively R3 divided by a short, which will be also shorting these two resistors. And you divide actually by a 0, so you get actually 1 plus R3 over 0, which is then approaching an infinite value. This is of course an ideal case. It will never reach infinite value. It will always look at the power supply of the operational amplifier, and that's our limit. Okay, let's now see the numerical values. So I will put here some values for R1, R2, and R3, and also the capacitor. So 1 kilo ohm, 2 kilo ohms, 7 kilo ohms, and 10 nanofarads for the capacitor. Now let's calculate now the DC gain first, using this formula, so 1 plus and then 2000 plus 7000 over 1000, that will be exactly 10, so 1 plus actually 9, and that is then in dBs, 20 dB, so you do 20 local of that, and you get 20 dB. How about Zn? Well, substitute the values here for the R1, R2, and R3, you get here exactly 2100 ohm or 2.1 kilo ohm. And how about the zero frequency? Again, using this formula, you know the C from the given here, and also Zn is calculated, so you get here 47,619 radians per second. And that will be then in hertz, so you divide by 2 pi, almost 7.6 kilohertz. Okay, that's our zero frequency. So our DC gain is 20 dB, and our zero frequency here is approximately 7.6 kilohertz. We will see how that works out in the body plot. So we have the gain on the vertical axis, and you have the frequency omega in the horizontal axis. You have here the zero line, but the gain starts already at 20 dB, which is our DC gain. And then at that zero frequency, omega z, it will then start to increase with a slope of 20 dB per decade because of that zero. If that was a pole, it will then decrease with a slope of minus 20 dB per decade. That is actually the effect of a pole or a zero. So the zero will then make that increase by 20 dB per decade. Okay, that's actually the result here. Let's see that also in the simulations. This is the body plot. Actually, this is our circuit, and this is the circuit drawn in the simulator. You see the operation amplifier, ideal, input voltage, R1, R2, and R3, and our capacitor C we have chosen. You see here the DC gain, and also the gain for specific dBs. Let me bring up our results, the zero frequency and the DC gain. We know it is 20 dB or DC gain. You see that exactly also here, so that is correct. Here I look actually at the gain, which is then going 3.01 dB above the DC gain. That is actually how you define the zero frequency. And that happens at 7.579 kilohertz, which is then exactly as we have calculated. So this is indeed correct. So that's good. Okay. We can also look at the situation by using our classical way of calculating the transfer functions. So I will do that. So I will not use the X element theorem now, and I work it out using the standard classical methods and then compare the results. So I will start first with the designated current here, so the I3 going light way. This is the current through the capacitors, IC, and this is the current through the resistor R2. And there's also a current here, which is then I1. but they are exactly equal to each other. Why? Because there's no current flow in the op-amp input terminals. This node here I will designate as X, and this node I will designate as Y. So I will use here now two nodes. I will use then Kirchhoff's current law. So I will first do the Kirchhoff's current law at node X. That means I3 will split in IC and I2. So that's actually what I do here. And now I will use capital letters. They are not DC, but they are actually the frequency elements. So I3 is equal to I2 plus IC. And that is then this voltage, again, capital letters for the frequency parameters. So VO minus Vx over R2, that's the left side, is equal to Vx over the impedance of this capacitor, which is then shown here. So this capacitor, I mean, this 1 over the SC. And there is also this current here, which is then the Vx divided by the series combination of R1 and R2. That's also I2. That's actually this term here. Now we can now see that we divide by a fraction, so we can multiply that by SC to Vx, so we have this expression. Now we can now collect the terms with the Vx, so we can do that in the next step. So VO over R3 we can leave it on the left side, and the minus Vx over R3 we can bring to the right side, and also put everything in the parentheses where you see the Vx. So Vx will be taken out, and you get to 1 over R plus R2 and 1 over R3 moving from the left to the right, and it will be a positive, and you get here SC here, everything in the parentheses. You see already some expression where you need the VO, but there is a Vx here which needs to be replaced because we need a VO over Vi expression, not a VO over Vx expression. But let's designate this here as an equation number 1. What I also will do is, that's the following step, I will also multiply everything left and right by R3. So you get here R3, you get here 1, and you get also here R3. So everything will be then multiplied by R3. So let's designate this equation number 1. Next one is using Kirchhoff's current law now at node Y. This is much simpler because I2 is equal to I1. That's what you should see here. So I1 is equal to I2 or I2 is equal to I1, doesn't matter. So you get here Y terminal, so the voltage here at this node, Vy over R1 is equal to Vx minus Vy over R2. That's this expression here. But we know due to negative feedback, we have discussed this before, that the voltage at this node, non-inverting input, and the inverting input should be, of course, equal to each other. That is because of the negative feedback here. So op-amp tries to make these two nodes equal to each other. That means the Vy is equal to Vi. So Vi is equal to Vy. So if this is 1 volt, it will be also 1 volt here. Now we can say, let's replace then Vy by Vi. So Vx is still there, but only the Vy will be Vi. This is of course handy because I don't want to have any new parameters. So the Vi is here much handy to use. And I can now do the cross multiplication. So Vi times R2, that's the left side, times the R1 is equal to R1 times the Vx minus Vy. That's Vi. That's actually shown here. Now let's work out the parentheses and collect the terms on the left side for Vi. That's what you see here. So I have now minus Vi times R1 to the left. And I can now divide by the R1, left and right hand side. So I have an expression for Vx, which is actually what I want to replace here. So this is equation number 2. So trivially, the next step is substitute this equation number 2 in this equation number 1. And then you get this expression where you see here the replaced expression for Vx. And everything here is the exact same as before. Now what can we do? We can do the following. We can divide by the Vi, of course. So we have a ratio. That's exactly what we want. And we can bring here the R1 and R2 together inside the parentheses. So for each term here, we can multiply that by R1 plus R2. And that will be then, this will disappear. This will be then multiplied by R1 plus R2. And this is also multiplied by R1 plus R2 as a summation. I will leave the 1 over R1 outside. That will be more convenient. You will also see why. So this will be then R1 plus R2 times this. So you will only have R3 here. This will be then here times 1. So you get the exact same here. And this will be multiplied by the summation here. That's actually also what you see here. What we also see is that this is a summation of 3 terms that can be also taken outside. I can also do that by dividing out this complete theorem by the summation of these 3 resistors. This is actually the next step. And this is done in order to see the time constant, so the zero frequency, much clearly. You don't have to do that, but it is more convenient. Now you have this expression, and you see also here the tau, which is our time constant in front of this S. So our zero frequency is then more clearly seen, and you can also work out this a little bit more clearly because you see here R1 and R1, that will be then 1, and you have actually here R2 and R3 here divided by R1 still. And if you look at this expression, and the expression we have found using the extra element theorem is exactly the same. See that actually. So this is actually a nice result. So we have compared now the transfer function using the extra element theorem and the transfer function we have found using the standard circuit analysis. The extra element theorem is much more structured, and for more complex circuit it is also more convenient to use. Of course, you can still go for the standard circuit analysis if you're familiar with how to deal with setting up the equations, but the power of extra element theorem is that you need to really follow some strict steps and you will find the transfer function much easily and faster than the standard circuit analysis. That's actually the power, and that's also the purpose to compare that with the method I have shown here. Alright, it was our example considering the extra element theorem applied on this op-amp circuit having a capacitive feedback, and we have also compared that using the standard circuit analysis here. And also show you the simulation result, and they were matching our calculations. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.